optimization problems first. Optimization problems. Okay, this is the first problem is let me try to find out. Yes. So this is application of calculus, right? I remember the problem on the test is a cylinder inscribed in the is a cylinder inscribed in the cone. Some students just draw the picture, did not do anything, so it's hard to set up in right the function to maximize the volume of the cylinder. Okay, so let's do let's look at the following problem. A rectangular box with a dimension A and B and C has a volume. This is A and B and C. Okay, and the volume is given, is fixed. It's going to be 4/3 square cubic units. All right, and we also know that B equals 3A. Okay, find the dimension that will minimize the surface area. Right. So you draw the picture, right? What you should do next step? Find the formula for the surface area. So write down what you're given. So A, B, C equals 4/3. Okay. This is a given, the volume. Okay. We also given B equals 3A. Okay. Then the surface area is going to be, we have a 2AB. I think a 2AC and 2BC. Yeah, we have a total of 6 faces. Right? That's the surface area. And then you have 3 variables here. Actually, you will get only 1 variable in the surface area. So you can easily use the calculus of 1 variable to minimize the surface, to find the minimum value. So look at the above condition. B equals 3A, so I can get rid of B, okay? Because B equals 3A, the volume is going to be 3A squared, and C equals 4/3, right? Then the surface area is also simplified, and 3A, right? 2A, 3A, 2AC, 2B, B is a 3A, C. So let's see. What I'm going to get is going to 6A squared plus 8AC. Okay. So now surface area is just function of 2 variables. But the volume is going to be 3A squared C 4/3. So from the above formula, you can also get C equals 4/9 and the A squared, right? So you use that to, yeah, then the area is going to be 6A squared plus 8A. C is going to be 4/9 and A squared. Okay, so you simplify it, you get something like that. It's only 1 function. Okay, then just find the minimum value of this function. This function has a minimum value because when A approaches 0, it is infinity. When A approaches infinity, it's also infinity. So the graph looks like that. Right? Here's the A. This is a capital A. So clearly somewhere there's a critical number, and it gives you the minimum value of the surface area. Let's simplify it a little bit. I'm not going to multiply this out, and this is going to be a to the negative 1, right? Right. So let's find the derivative. 6 times 2 times a plus, it's minus now. Right, that's going to be 0. Right, so now we have to simplify it. Right. So you multiply both sides by a square. So you get 6 times 2 a cubed, and that's going to be right. So a cubed equals, we have to simplify, right? So 8, 4, 9, and 6 times 2. So let's simplify. I think I'm going to get 827 over 27. Yes. So from here, a is going to be 2 over 3. So you find the value for a. So then you get b, right? That implies b equals 3a. So it's going to be 2. Okay. And the c, remember c is going to be 4 over 9a squared. C is 4 over 9 a squared. A squared is in the denominator, so I'm going to get 3 over 2 squared. So actually is 1. So you get the dimensions that minimize the volume, minimize the surface area. Now I want to discuss the problem on the test. Right, the same, similar problems. I put this problem on the test. Actually, I did the same problem. I'm not sure it's a review problem. Yeah, in my review notes. This similar problem is already discussed. A cone and a drawer still in the inside, and but the h and the height are not specified. Okay. So let's see. Let me check whether I did it or not. Okay, this is my previous notes. I'm not sure this is this. No. Yeah, test 2. No, it's not here. I think it's in the notes for during the class. Yeah, for that section. All right, so let's look at the problem. All right, find the largest possible volume of cylinder that is inscribed in this cone. All right, so the height is 6, the radius 3. All right. Find the largest possible volume of the cylinder. Okay, inside this cone. All right, the cone is fixed, right? So how do you find the volume of cylinder? Well, if the cylinder has a radius r and h is height, so the volume of cylinder is going to be pi r square h. No choice, right? If there's no restriction on I and h, then this can be as large as possible. So I and h are related. How can I relate? Well, look at this cross section. Right? This is R. This is H. Here's a 3. This is a 6. right? That's the geometry, right? Similarity of triangles. This is required for this calculus course. Similarity of triangles. There are many. There's problems about related rates, about optimization problems. It involves triangles. Yeah, maybe you have to use similarity. So H and R are not arbitrary; they're related because they're sitting in this triangle, right? So you have to find the relation between H and R. That's not given directly. So how do you do that? Well, use this smaller triangle is similar to the larger triangle. Now, what is this? It's a 6 minus h, right? Because the whole height is 6, and then subtract the height of the cylinder. Then you get the height of that triangle. So this is a triangle I'm using. I put it aside. So this smaller triangle is similar to the larger triangle. So therefore, 6 minus h over 6 is going to be r over 3. The ratio of the corresponding sides are equal. The ratio of the corresponding sides are equal. Okay. So now you can, what do you have to do? I think that you have to solve for h. Yeah, it's better because r square, you can, if you solve for r, then you get a function of h. If you solve for h, you get a function of r. It doesn't matter, right? Okay. So what we should do? I think let's modify it, right? Modify both sides. So 6 minus h is going to 2. Right? I think I'm going to solve for h. So h is going to be 6 minus 2r. Okay, so volume is going to be pi r squared, 6 minus 2r. So if I take a 2 out, and that will be 3 minus r. So the largest possible value for r is going to be 3. The smallest value for r is 0. Why? Because it's a cylinder in the cone. Okay. And you look at the function. You look at this function. Here's r. Here's a v. When I is 0, v 0. When I is 3, it's 0. So it looks like that. Right? So somewhere it has a maximum value. Right? When I equals 0, v 0, because I equals 0, v 0. Right? So I have to define the derivatives. Once you get the formula, you can do the rest of it. Right? So v equals 2 pi 3r squared r cubed. I'm going to find the derivative. It's 6r minus 3r squared. Okay. So you take okay. So you start, let's r to be 0. So r equals 2. So here's 2. Right? So the volume has an absolute maximum value. So the volume has a maximum value at I equals 2. Right? When I equals 2, then h is going to be h is 6 minus 2, 2 is going to be also 2. Right? So h and the height should be the same. Right? So we solve the problem. No, we haven't found the maximum volume yet. So we only find the dimensions of the cylinder. Okay? So the volume is going to be pi r squared h. So pi 2 squared is 2. And that's going to be 8 pi cubic units. So this will be the answer. Okay? So ask yourself, which part is difficult for you, right? Say, you can find the volume formula for the cylinder. You should know the volume formula for the cylinder. But then it involves two variables. It involves two variables, I and H. So you have to find the relation between I and IH, then you draw the picture. Okay? Then you draw the picture, you find this is the important relationship using similarity. Maybe this is a difficult part, the geometry part. Okay. Another problem related to the geometry is the bonus problem. Now, if you have a time, do the bonus problem. There are not many points. One problem only half of the credits. If it's regular problem, maybe 8 points, but the bonus one only 4 points. But there's 2 bonus problems there. If you have a time, you have to do it because that gives you extra points for the, so your final score, it's kind of inflated a little bit. Okay, so we give the extra bonus point. So this is from 4 points. The base of the triangle. This is a triangle. Okay. The base of triangle is increasing at a rate of 1 centimeter per minute, while the area is decreasing. That is a rate of 10 square centimeters per minute. My question is, at what rate is the height changing? Okay, so there's an addition condition that when the base is 20 centimeters, and maybe those are the unnecessary condition, but they give you this information. All right, so that's a question. The first thing, you draw the picture, right? And you have a height, and that's a base, B. So the area is going to be half of the H square, H just H. So majority of students, almost 99% of students can know this formula, except for only one student did not know the formula for the area of the triangle. Give me the last one, yeah. So I said, "Are you graduate from high school?" No, just kidding. Right? This is you have to know this formula. We're not going to. Like a surface area of a cylinder, maybe you should be able to try to find it if you forget. Okay. Surface area of a cylinder, right? So this is a area formula. So all these quantities, 3 quantities are related. Okay. 3 quantities are related. They keep changing. You cannot put the specific numbers right now. They're changing. So when you differentiate, right, that's a function of a t. So you differentiate with respect to t. Then by the chain, by the product rule, right? Okay. So that is the formula. All the functions are functions of t here. So we know the base is increasing at the 1, and we are given the following thing. So we get the area is decreasing at 10 square centimeters per minute. The base, right? The base is increasing at the rate of 1 centimeter per minute. It's positive. And we want to find out the rate of change. We want to find out at what rate the height is changing. Okay, so this is the way we find out. So think about, look at this, right? If you multiply both sides by 2, I get a negative 20 equals h plus b dh d. Okay. So this is general identity. So you can also, you can modify it at the moment when, in general, you cannot uniquely determine the, the derivative of h with respect to t, because that depends on h and t. So at the moment, this is only the last minute you can put a specific value. So when b equals 20, h equals 10, right? Then you get h equals 10, b is 20. Then you can find the rate of change in the height. So that is going to be negative 30 divided by 20. So it's negative 1.5 centimeters. So it's the height is decreasing. Right, the height is decreasing because the area is decreasing. You know that even the base is increasing, but increase too slow. So you have to make the height decreasing. So this is the problem. Do you think it's difficult? It's not difficult. If you understand the mathematics part, you write down the formula and you differentiate. Right. So those are the two problems. Use the geometry a little bit. The next group of problems is find the area or the volume of some region. This is sometimes you just need to set up an integral. Sometimes you have to evaluate the integral. So sketch the graph. Sketch the region increased by y equals square x, y equals x squared. Then find the area. Right. So we have to sketch the graph. Just sketch. You don't even make it precise. So y equals square x looks like that. Y equals x squared. Okay, so there is the intersection here. And clearly the intersection is 1 and 1. So this is the area. This is the region. Yeah, I have to find the area. Okay, so it's y. Okay. For practice, I just want to set up two integral in this case. Okay. I want to use the vertical lines. If I use the vertical lines to cross, so that will be x. Okay. So this will be the length will be ln x. So the area is going to be integral from 0 to 1 ln x dx. Right. What is ln x dx means? This is means the area that one small strips. So you ln x is length times the width tells you the area of that strip. You add them together is the integral. Then you get the total area. Okay. So you have to express the length of this piece. The length of this piece, because both functions are expressed by x squared, right? Y equals x squared. Which one's on top? Square of x. So ln x equals square of x minus x squared. Y equals x squared is a curve below that. So the difference is going to be area is going to be integral dx. Okay. Let's find the antiderivative of this. Antiderivative is going to be when all right. So that is going to be 2 over 3 x 3 over 2 minus 1 over 3 x cubed. So you just need to plug 1 for x to get the answer. Okay, so this is the area. But you can also use the horizontal line, okay, to evaluate this integral. So you get similar integrals. My next question is, so R is bounded by this graph, okay? Let R be the region bounded by y equals square x, y equals 1, and x equals 0. So set up the integral for the volume, okay, of the solid generated by either way, by rotating about the x-axis or rotating about the y-axis. The first case, okay, this is a rotation is about about the y-axis. Right, the rotation is about y-axis. I want to use three integrals for the same volume. So actually, there are four integrals you can set up. So let's draw the graph, and using the cylindrical shells or using the discs. So this is a graph, right? Y equals 1, x equals 0. Okay, be careful when you draw the graph. Some students after finish that, they forgot which region. That's region this top, this pole. Okay. Not the one under that. Okay. So it's rotated about y-axis. That's it, right? Draw kind of 3D picture. Sketch it. Okay. Can you use the discs and the cylindrical shells, both method, to set up the integral? Okay. All right, so let's use the disks. So the first method, right, 1A, right, using, yeah, you have to learn all those methods because it's possible we are asking you to use a specific method to set up integral. Okay, you cannot, yeah. So use disks. How to use this? Then you have to cut the solid in that way, right? Disks. Right? So this family of disks depends on Y variable. Depends on Y variable. Right? It depends on Y variable. So the volume is integral, and this will be A over Y. That's Y variable, right? Okay, what does AY dy mean? AY dy means is the volume of this one slide. This one slide. The thickness is dy. So y starts from 0 to 1. Clear. It's 1. Right? And you have to find out what is AY. It's going to be pi r squared. Right? R is going to be the radius. And what is the radius? And you choose that special point, x and the y. So R is going to be just x. Right? Now, you have to express x in terms of y variable, right? Because this is a point on the curve, y equals square x. So x is just equal to y squared, okay? Because y equals square x, okay? So now you plug them into the formula. You get pi r squared, which is y, then square and dy. So this is the integral for this volume. Okay, let's do the next one. Right, this is a picture, right? Okay. Let's use cylindrical shells. The solid is this. So when you draw the cylindrical shells, you get a cylinder here, right? Imagine. It's not under that. So here's the R, that's H. So this is the reference point, maybe X and Y. This is the original curve. All right. So the volume is going to be 2 pi R H dr. So R, the smallest value for I is 0, the largest value for I is 1. Right. So let's express what is R. R is going to be X. What is H? H is 1 minus 1. Yeah, if you're using the coordinates at that point, H is 1 minus 1. All right, so which variable I'm going to use? I can use R, I can also use X. So if I use the X, so Y is going to be square root of X, right? Then, since I is equal to X, that's why you don't need to make any change. So equals I is going to be X, and 1 minus square root of X, and then dx. Okay, then. Now, if you want to say, I don't want the X, I want the Y variable, it's fine. If you use the Y variable, it's more complicated because the relationship between I and the Y is not clear, right? Yeah, so you see that I equals X, X is going to be Y squared, okay? And H is going to be 1 minus Y, perfect. You don't need it, right? So when R runs from 0 to 1, Y runs from 0 to 1, okay? So dr equals 2y dy. So the volume can be also have an integral, but usually people don't do that, okay? But it's possible. Y starts from 0 to 1, 2 pi, I is going to be y squared, and H is 1 minus y, and di is 2y dy. Now this is very complicated. very complicated function, but I guarantee you, this will be the same value, give you the same value. Okay. All right, so now the second part is about the x-axis. Right? The notation is about the x-axis. Right? This is a region, right? Okay. So if you look at about the x-axis, you get a picture like that. Right? Can you use the disk or cylinder shells using disks to set up an integral? Can you do that? So try this. Yeah, can you set up an integral for using disks? So use disks, you have to cut it in that way, right? So there was actually two disks. One is inside and the one is outside. So you needed to, this is little r, this will be the capital R. So volume is going to be integral A. If you use this, it will be AY dy. Okay. No, x dx. Why? Because that's this femoral discs depends on the x parameter. Right. So AX is going to be pi capital R squared minus pi little r squared. Okay. This is origin the point, so I use the x and y. So I is going to be y, right? Capital R, so y is square x. Capital R is always equal to 1. Okay. So then the volume is going to be pi 1 square by pi square x square dx. Okay. Okay, so the second method uses cylindrical shells. Okay, so here I have to, this is the original piece, right? It's not changed yet. So the cylinder I'm going to draw will be here. Right? So this is a cylinder. So that will be the radius R. And this is the height, H. And this is a point on the curve. So look at this, right? I is going to be Y variable. Okay. H is going to be X. And X is going to be Y squared. Now, if you want to use a Y variable. So the volume is going to be 2 pi R H d R. The smallest radius is 0, the largest radius is 1. Right? Now, you can use the Y variable for the integral because I equals Y, right? So that's why it's going to be 0, 2 pi Y, H is Y squared, and dy is just dy, Y from 0 to. Good. So if you are able to understand this problem is 4 different methods, then you're okay with this type of problem, that type of integral, okay? So you can try to solve it without looking at my solutions by yourself to see if you're able to set up an integral, okay? When you have time. Show that the equation can x plus cos x has exactly one real root. A real root means if you let the function f of x to be 10x cosine cosines, right? So actually again find the zeros, right? So if you look at the graph, okay, maybe the function looks like that. And now this have 3 roots, right? So it's not shouldn't be like that. Maybe like that, right? That's only one real root. Okay, this is the y equals to f of x. To prove that it has exactly only one real root means to prove that it has exactly has one x-intercept. So first we have to prove at least there's one x-intercept, right? And second, then you prove that it has no more than one x-intercept. So clearly f, let's choose a larger value, f1, okay? That's 10 plus cosine 1, which is greater than equal to 10 minus 1, which is 9. That's greater than 1, 9. And f negative 1, okay? It's going to be negative 10 plus cosine negative 1. Okay, this will be less than equal to negative 10 plus 1, which is negative 9. right? So what does that mean? That means f has the opposite sign. That's to end point. So then there is at least one number c in the interval from negative to positive 1 such that f of c equals 0, right? Because that's one end, this is going to be negative, you know, negative 1 f of 1, negative 1, right? It's negative. The other end is positive, f of 1 and f of 1. So it's harder to draw it. Right, so one end is positive, other one is negative, then somewhere between them, you know, there's the x-intercept. All right. But on the other hand, the derivative of sine x is going to be 10 minus sine x, okay, which is greater than or equal to 9. So that means f of x is always increasing. Increasing means you cannot have more than 2 roots, okay? So this implies h of x does not have more than 2 roots. No, it does not have more than 1 root, but 2 roots. Compels. Right. So, you know, because it's increasing, if it has 2 roots, it goes like that. Okay, it's not increasing, right? Going up and down, right? That's impossible, right? Because it keeps going up. So we're dead. First of all, we show that there's at least 1 root. Then second, we show that it cannot have more than 1. Otherwise, it's not going to be increasing. Look at the picture. You know, if they have a 2 x-intercepts, then it's not increasing. All right, so the next one is we are given the function 1 plus x minus 2 over x squared. Sketch the graph. Yeah, what is the most efficient way to sketch graph? I suggest finding the derivative at the end. You know, don't do that too early. Okay, you can sketch the graph without using the derivatives. So take a look at this. Okay, I probably have to find the intercept first. There's no y-intercept because it's asymptotus, right? Let's look at the asymptotus first here. At asymptotus x equals 0, that's a vertical one. Right? And the horizontal one is y equals 1. Why? Because f of x equals 1 plus x minus 2 of x. This approaches 1 as x approaches plus minus infinity. X minus 2 divided by x squared approaches 0. Okay? When x is getting larger and larger. So that's the reason, yes. Okay. Now, yeah, you can rewrite this function in the form like x squared plus x minus 2. Okay, so that gives you x plus 2 and x minus 1. Clearly, when f of x equals 0, x is going to be negative 2 and 1, those are the x-intercepts. Okay, the graph passing through those 2 points. I think we are almost done to get the graph. Okay. I have to look at the behavior nearby the vertical asymptote. For x close to x equals 0. Okay, y equals f of x is close to 0 plus 2, 0 minus 1 x squared, which is going to be negative 2 of x squared. So nearby this vertical line, it's going to be like this, similar to this. Okay. So let's draw the graph. 1, 2, negative 2, 1. Okay, then that's another horizontal line. Okay, nearby the y-axis, which is x equals 0, the graph looks like that. Negative 2 over x squared. Negative 2 over x squared is a graph like this. Okay, so think about that. This is a picture y equals negative 2 over x squared. Okay, so your graph should be similar to that. Y equals negative 2 over x squared is symmetric about y-axis. Okay, but here, of course, it's not exactly the same as negative 2 over y squared. So it'd be, it's not very symmetric. All right, so that's a picture. Right. My another question is, and this goes to negative infinity. Okay, my next question is whether this go up or down, or whether this go up or down. Right? It's possible, right? So I haven't found the derivatives yet. Okay, let's go back to function. Okay. So you think this graph has intersection with the horizontal asymptote y equals 1, and where if it is. In order to see if it has an intersection point, this just set it to be 1, right? Then you will see that you get x minus 2, x squared equals 0, that implies x equals 2. So I find out at that particular point, the graph has intersection with the horizontal asymptote. So now only at that point. So this side is the graph always below the horizontal asymptote. But this side have to go up. Once it go up, it must go down. So because this is a horizontal asymptote. So this is a graph, all right? Without using derivative, I cannot determine this highest point. Right? I know it's there. I cannot determine the points of inflection because this is a place where I change concavity. Why? And this side, left-hand side is always concave down, clear. So this side is the second derivative is always negative. And this here is the second derivative is negative. The problem is it approaches this horizontal line, so you have to concave up here. The second derivative must be positive here. So this is a point of inflection where the concavity changes. Otherwise, it does not approach the horizontal asymptote, right? Because once it goes through the horizontal asymptote and go up, right? And you want to make it coming back, you have to concave it down like that. Otherwise, it will have another intersection with the horizontal asymptote somewhere, right? Right. So from the graph I got, I know there's one absolute maximum value. Then there's one point of infraction. In order to find that, we have to find a derivative and a second derivative. Okay, let's do it. How to find a derivative? Which expression we have to use? Okay, it's a little bit difficult, complicated to find a derivative, but we can do that. Constant. Yeah, to determine the maximum point and the inflection point, we have to compute the derivative. Yeah, we have to study the equation. Okay, those two equations. The first equation gives a critical number at which the function is absolute maximum value. Okay, let's look at the derivative. How can I do that? Well, f prime x, and it's going to be x minus 2x squared prime, right? And that is going to be x to the fourth. I think we can cancel x and x. All right, so this is the simplified version. All right, we find out if that set this to be 0, x equals 4. Okay, so this is a place where you get the maximum point. So maximum point so this is a maximum value of the function, okay? Where it is appeared somewhere in 4, right? So let's go back to the picture. So this is a point when x equals 4, okay? 4 and yeah, 4 and the 1 and 8. Okay, so this will be the maximum value. So the inflection point should be on the right-hand side of this. So you have to find the second derivative. Okay. Right, let's simplify it. I get negative x cubed. Negative, negative becomes positive 3x cubed minus 12x squared. Okay, I get, then I get 2x cubed minus 12x squared, x to 6. Then I divide by, I take a 2 out, and x minus 6. Right, so this is going to be 0 when x equals 6. Great. So the points of infraction, you have to find the y value. Okay. So you will get 1 plus 4 over 39, and the 1 plus 1 over 9, and the 1 over 1 over 9. So smaller than the absolute maximum value. That's obvious. Okay. So you get the infraction point has coordinates 6, 1 over 1. Right. And I already predicted there is an infraction from the picture at the end, right? So we remember. Yeah. So remember, right? This is a picture, right? This is horizontal, right? Right. And this is 1, 2, right? And here's 1. You have to go. See, this is a concave up, right? Concave down. Concave down. Let me show you. Okay. So now, if it's always concave down, then it will intersect the horizontal asymptote again. So you have to bend it this way a little bit, right? If you make something, you have to bend it. So there's a point of an infraction. Okay, and this is the maximum point. So I knew that at the very beginning, but I just don't know the exact location. So you have to use a derivative to find it. So that's why I encourage you to sketch this graph without finding derivative. Number one is because you cannot trust yourself. You always make a correct computation by the derivative, right? And if you make a mistake, you screw up. You cannot continue. You stop there because the data you got is wrong. How can you schedule graph based on wrong data, right? So it's better to find schedule graph without using the derivatives, okay? And then you find the, tells you get the exact location of the points. Okay. So that's a whole page, 12 points for this problem. You're given enough space. Okay, there are some points, there's some problems you can easily get a point, and just be careful, like find the derivatives, because after so many exercises you've done, find the derivative, don't make mistakes. Okay. And you should know the definition for the integral, and the definition for the derivative. Right? The definition for the derivative for the integral is also is the limit of the Riemann sums. Right? The definition for the derivative is the limit of f(x plus h) minus f of x divided by h, and you find the limit. So if you ask it to use a definition to do the problem, don't use formulas to do that. Okay. I will continue to discuss the problems using another set of